Well, welcome to the Developer Conference. I guess you were welcomed upstairs or in the keynote overflow room, but welcome to the visualization track. My name is Jim Jeffers. I lead our HPC visualization team at Intel, working on this area that we've been calling software-defined visualization. I see some friends and hopefully some new friends in the audience. And so we're going to have, over the next 2 days, we're going to have several talks and as you can see, some demos as well available to look at and discuss. So first, thanks for coming. Just to give you an idea of what we're doing, the visualization elements, because it's mixed up between certain rooms. Now today, the good news is all the visualization track is in this room today. So that'll be easy. Just come back to this room. I'm going to talk briefly, and then we'll talk about OpenSWR, Osprey, and then we'll talk about some of the integrations of our libraries into other well-known applications. And then finally, just make sure you're back around. We'll be able to do probably most of our Q&A. We might go pretty quick through the talks, but our Q&A and just discussion will happen here tonight from, I guess we have from 5 till 8, but from whenever the end of the, I guess, keynote today. I think James Reiner is going to do that again, but we'll be in here hanging around with a beer or two, and we can talk about, give you guys actually a preview of many of these demos are going to head to the SC floor. So. Tomorrow is when things kind of change around a little bit. After the first in Bill Magro's keynote, there will be a little blip about pulling things together with visualization. So look for that. And then Paul Navratil will be doing a Vis lab on the integration of what we call PV Osprey, or an Osprey plugin into ParaView. And then that will continue for 1.5 sessions, and then it'll shift over to the Senate room, or what's called the IPCC room, and there we'll talk about what's going on with visualization, and then several other case studies, and then end with Kitware talking about the integration of Osprey and OpenSWR into ParaView, which was announced by Kitware this week. And then just finally, there's a gap where there's really no Viz things going on, so feel free to obviously go to the other sessions, and then we'll close the day, and then as you heard, you're invited to the networking reception. So now I'm going to talk about kind of give you a quick overview of what we've been doing with what we call software-defined visualization. And then we're going to have some deep dives into the libraries that are behind it and learn more about that. But this really states the real goals that we have with implementing software-defined visualization. So one goal is the knowledge that data is getting larger and larger and more complex. Actually, as Christina was mentioning upstairs, if you saw what she was talking about, where they did a massive data processing on Blue Waters, and then they had to try to figure out how to get it to a Vis location that was taking weeks, even months to do. So we want to handle that so that turnaround time is much quicker for that. We want to enable on general purpose processors, so truly software defined without the need, again, to push data around to GPU specific clusters, which again bring issues in, which we'll talk a little bit more about. And then finally, we're very focused on delivering open source software solutions and also enabling a high level of collaboration with the ecosystem. So that's kind of an overview of what our goals are. Why are we doing this? How did we get here? So a brief history of what we call SDVis, or software-defined Vis. Why did Intel kind of embark on this? Well, sort of around the time when we were looking at deploying what's now our Intel Xeon Phi coprocessor, codenamed Knight's Corner, we also began to get some people in the community, the Vis community, reaching out to us saying, is there a way to use these things for visualization? We have some serious concerns about where the state of visualization is. In particular, the fact that it was very GPU-centric. Therefore, the data sizes really had to somehow be figured out how to fit into a GPU and GPU memory. And OpenGL alone was really dictating what the visual quality is, although some people were dabbling in ray tracing, including John Stone, who's in the back there, one of the leaders in bringing ray tracing quality into the picture. Visualization tools themselves, the key tools like ParaView and Visit and other tools really weren't, seemed to be on the roadmap of improving at the rate that parallelism, CPU-based parallelism was there. Now, in some cases, people didn't have access to GPU clusters, so you still did have MESA, the MESA platform, but that really had almost no chance at interactivity, at least the level of interactivity to get insight from your science. As I said, people dabbling with Manta in ParaView and VMD, but really not the performance there. Simultaneously, in the 2012-2013 timeframe, our Intel Labs team had created very high-performing parallel ray tracing libraries that are called Embry. That is still, as you'll see in a second, a vibrant project that we are running, and they really put the effort into the low-level, high-performance parallelism needed for ray tracing. And it got a lot of traction in the industry, particularly what we call the professional rendering industry, like the movie industry and animation. So there was this core technology in ray tracing. There was this disk that was high-performing, a disconnect, though, in the scientific Viz community where it was all OpenGL based, and ultimately people were looking for the highest quality imagery to really get the most insight. And then with all that data, we saw an opportunity to engage and take advantage of the growing clusters, the cluster sizes, and as things moved to exascale, there was going to be this challenge of really enabling the scientists to gain insight from their data, at least data that they wanted to see visualized. So about 2 years ago, we started pulling together a team with concepts from Ingo Wald from our team and the Embry team, and then collaborators like TAC and Kitware, who saw an opportunity to kind of change and make the momentum towards modernizing the code. So the other thing we did is you've probably heard of the Intel Parallel Compute Center program. That was engaged as well, and we actually got three, all who are here, visualization centers or teams who were heavy into the visualization enabling arena, as well as a number of IPCCs who were doing other work, but visualization was an important part of it. We'll talk about all of those in a second. And then finally, we really announced just about a little over a year ago the fact that we were doing this effort and looking for collaborators and partners, and hopefully we'll see what the fruition of that is over the next couple days. So probably preaching to the choir, but many people think visualization is really foundational to gaining insight, particularly for scientific data. Our humans are oriented towards visualizing things or visual use of our eyes and visualization, and how we map to it is one of the key areas of unlocking and gaining insight. Therefore, large-scale visualization is pretty widespread. We've got academics and researchers, which is probably many of the folks here, but you have designers and architects. You've got life scientists, engineers, and obviously the film industry leading the way with ray tracing and with high-quality Viz. So anybody who wants the most realistic, insightful information really wants and needs to use Vis, again, particularly at a large scale, higher quality, a larger amount of data. Again, this is sort of a repeat from before, but a different look. But really, our visualization solutions that we've put together with our partners, which we're going to talk about today and tomorrow, the goal is really to enable that deeper understanding, use the parallelism that's in the machine to bring that about, and then utilize open source for more and more collaboration so that people are, one, comfortable with the solutions, and two, can adapt the solutions to their specific needs and not have to sort of go to the well or license something special, whatever. And then finally, without the costs of a dedicated GPU rendering solution. And by cost, we not only mean dollar cost, but the cost of moving data and managing those systems. And basically, if they're GPU and really meant for visualization only, then you're not taking advantage of the compute capability of the associated processors. So the bottom line is again, we engaged in this because we knew, and that we have been adding more and more parallelism with each generation, as well as the many-core parallelism that we have. So, you know, we have great parallel processors that also present themselves as general purpose hardware solutions. Visualization is obviously pretty embarrassingly parallel, and our processors, both Xeon and Xeon Phi, are excellent platforms for that, because rendering really is just another kind of compute problem. And that's really what it boils down to. In rendering, we're doing parallel compute, and we have, we believe, the best parallel compute solutions out there. So again, this is a typical view of today's setup in medium to large scale HPC clusters, where there's a carved off visualization cluster as well as a large compute cluster. And the problem with that situation is really the bottlenecks and the turnaround time and all the issues of I/O and transferring data, managing it as a related but separate cluster with different queues, and that leads to a lot of headaches. And that's one of the reasons we heard from a lot of people that was a real headache in managing and dealing with systems and trying to get the viz that they really wanted to. The other thing is you know, data size matters. Actually, I don't know, your thing is not running there, Aaron. This is actually from work from Aaron Knoll in conjunction with Ingo Wald. And the reason I'm complaining is there it is running live, the same data set that's up here. It's a little fuzzy kind of because of that, but you can see the level of quality that Aaron has. And that is the 12 billion particle data set, right? Oh, he upped it just for us. At the time, this was 12 billion. So he's got 30 billion particles that can actually be interacted with live on a single workstation machine, although a very powerful E7-based machine with 3 terabytes of data. But to enable that manipulation, it just never would work on a GPU-based system. And that kind of massive data on either large workstations or being able to distribute across a cluster that obviously has that kind of size of memory that Christina was talking about in the keynote is critical. And enabling that is really what we're after. The other beauty of SDVis is it's very, very flexible. It'll work at every scale from a laptop all the way up to large computers, and we're trying to enable all that capability as well. Again, this is sort of the challenge. This is the solution that we're targeting, which is basically you have a general purpose compute cluster that is also your visualization cluster. And then when you have that situation, you have all the flexibility in the world. If you want to carve off for a moment, a week, a month, a quarter of the system to do visualization, and at least have faster, more cohesive I/O, you can do that. It also enables use models and improved use models like in situ, where you can do your simulation and simultaneously do the visualization so you can see where things are going. So you have all the flexibility and eliminate some of those bottlenecks. You reduce I/O movement. Your resources can be allocated in a more standard way. And again, you don't need the management of the cluster. You get all your capability out of that. A mini version of that also is in the back, the last system there at the tail end to your right, if you look at it, is a cluster. It's a small Xeon cluster, 4 nodes, but we can talk to you about the cluster software we have that's actually doing distributed rendering, basically enabling either higher frame rates or better quality based on how many nodes that you have access to. So when we thought about how we would do this approach and how we could best meet the needs, from that feedback we got, we really realized that we had 2 options. One, we had a strong ray tracing, fidelity, photorealistic environment with Embry that already was working well. We had some dabbling with that, like I said, with VMD and other uses, primarily for publications to print out the best possible. But when it comes to interactivity, OpenGL was the standard. So we said, hey, we need to do both, okay? We need to enable legacy applications on clusters that were very targeted at OpenGL. It was basically the only game in town unless you were kind of rolling your own. And then secondly, we wanted to work with the community to enable the ray tracing capability in the environment in a way that was as seamless as possible. But it was new, and a lot of the architectures weren't built for the ray tracing, so we knew there'd be some work there. But we realized that in order to get the maximum performance and maximum insight and maximum benefit, that we would need to do both solutions. So in fact, that's what we have done. We have on your left, so my left, your left side of the screen there is sort of the traditional OpenGL path, and we enable that as well at a much higher performing, highly focused on the parallelism of your processor so that you get interactive performance where you didn't before with MESA. And that's OpenSWR, and we're going to talk about that deeply in a couple minutes when I get off of here. And then on the right-hand side is the ray tracing path with a distributed-based environment called Osprey, which we'll, again, learn more a lot today. Again, OpenSWR is basically an OpenGL drop-in. We are integrating it into MESA 3D, so it's basically an optional device path that you can use, and it has some really great performance, which Bruce is going to talk about in a second. And today we are already working with ParaView, Visit, and CEI Insight closely to make sure that we provide the features and capability and performance that those applications need. That's our focus. The Viz applications are our focus, not Twitch games or anything like that. We're not focused on that at all. We're making sure that these applications that everybody uses every day are well supported. Embry, as I mentioned, it's a kernel library. It's the ray tracing equivalent of what MKL or the math kernel library is, or something like Magma. And our team, we have some of the best experts, both in ray tracing and in optimizing for Intel architecture. So it's a great team we have that's implementing that low-level capability and making ray tracing a much more interactive environment. It's, again, it's an open source capability. Just to give you a sense of the impact and the performance of Embry, we did a paper in 2014 that was accepted for SIGGRAPH, and you'll see here that today's Haswell on a essentially exact duplicate path tracer renderer, the Haswell runs about 4x on at least this set of workloads here that we sort of picked at random. and for their availability of their models, but running this apples to apples comparison, we're getting dual socket Haswells with 18 cores being on the order of 4x a Titan Maxwell based GPU for many of these models. So, you know, in these models we have performance leadership, but we certainly are very competitive to more than competitive. The Xeon Phi, which is the current coprocessor, is now about a 3 or 3.5 year old architecture. I think you know Knight's Landing is coming. And even today, with the latest NVIDIA GPUs, we're running on the order of 2x of that capability at the low level ray tracing capability. Embry, again, is heavy adoption. This is a small subset of the people who have adopted Embry for their renderers. Osprey is our ray tracing engine. It's kind of a middleware rendering environment, and it adds a couple of things that Embry doesn't bring along with it. Embry is basically, you know, again, a core library. Osprey brings the capability to distribute it at any scale, up to very large scale rendering, as well as a very strong volume rendering capability that many of the demos are running right now are using. And the volume rendering is really a strong performance, and this gives you an idea of the type of applications we can run. Actually, no, none of them are here right now. I do have a movie of the cosmic microwave background. Again, we are integrating into VTK, ParaView, Visit, and VMD. If you haven't seen it, take a look at Kitware's recent press release of this past week where we talk about their integration of OpenSWR and Osprey into their environment. And we've also have a plugin for Osprey, which you'll see. It's actually running over here to the first one on the left there. Is what's called PV Osprey from TAC, and we're all working together to bring all these things to the best solution possible. Again, I'm almost out of time, so I'm going to go through. We can look at this later this evening. I can bring this up on my machine, but we've been working very closely with the Stephen Hawking Center for Theoretical Cosmology. So yes. That team is obviously a well-known cosmology team, and we are working on multiple projects with them. This past year, we helped them do a detailed analysis of the cosmic microwave background data from the Planck satellite, and they actually discovered some new science, which we can talk about later. And then we're also on the right here is the what they call domain walls. This data set is upwards of 10 terabytes, and we will be, there's a movie of it captured off of an SGI UV machine running all 10 terabytes interactively and manipulating it and zooming in and zooming out, and it gives them a really good sense of what the early universe was like. Sergey's going to talk about this tomorrow, so please go to his talk. And then Dave DeMauro will talk about you know, what we've been doing with Kitware and ParaView. Again, TAC has been a close partner in all of this and providing capabilities of integrating Osprey as well as testing SWR. University of Tennessee also, it's a lock over there, is running Visit, and Visit is one of the applications we're supporting, and there'll be a talk about that tomorrow. And then Sean's going to come up and talk about CEI Insight and the integration with OpenSWR. One up. And also working with John Stone and VMD. He'll be talking a little bit later, so I'm just going to plow through this and let Bruce talk about the real fun stuff. Finally, University of Utah is where we see the particle data. There's also some LiDAR data that's very cool, which we'll be looking at tonight. Some work with service engineering. Christian is here on using ray tracing both for simulation and rendering. And then you know Knight's Landing's coming. I'll give you a hint on the show floor. We're going to be showing a 8-node Knight's Landing cluster with our OmniPath fabric, actually running a more higher quality and more time step version of the MPOS over there. So we can come and talk about that, but its capabilities, I think, really are going to bode well for our visualization. And really, ultimately, we're trying to bring together a general purpose computing environment with these solutions. Now I'm going to let Bruce come in and talk about SWR and tell you more details about that. So thanks.
Oh, thanks, Jim. My name is Bruce Cherniak. I'm one of the key developers on OpenSWR, and Tim Rowley, sitting down here in the front row, is one of the other key developers. OpenSWR is a scalable, high-performance software rasterizer. Unlike ray tracing, we're doing the rasterization approach to SCIVIS. As Jim just mentioned, we have a couple of different pillars to support our SDVis initiative, and that is one of them is OpenSWR. As I just mentioned, is an OpenGL software rasterizer. The other, as Jim just mentioned, is Osprey. Osprey underneath uses the other software package that we have, which is Embry, the Embry kernels. But I'm going to focus on OpenGL and the OpenSWR package, open source package that we have. So a little bit of what we'll talk about is kind of why our motivation for doing this and our goals, some of the alpha progress that we've had. We're still in an alpha stage with it, and the alpha progress that we've had. We'll take a peek under the hood a little bit of kind of what makes SWR unique, what makes the SWR core well suited for scientific visualization. We'll look at the early results that we've gotten so far on some of the key applications, and we'll talk a little bit about next steps and open it up for comments and questions. So one of the main questions, I guess, is why another software rasterizer? In the visualization community, there's already kind of the de facto software rasterizer is the LLVM pipe that's built into MESA. But there are some unique differences between LLVM pipe and SWR that make SWR very well suited for scientific visualization. The first of which is our threading model. The LLVM pipe uses a single-threaded vertex processing model, and it should be easily configurable, but right now the back-end rasterization is limited to 16 threads. On the other hand, OpenSWR uses a common thread pool where we have one thread tied to the API, and it runs in the API space. The other threads, 1 through N, are available to pick up either front-end vertex processing or back-end fragment work as necessary. So we have a kind of a dynamic load balance of parallelization as opposed to just a single-threaded vertex processing. In vertex processing itself, in the LLVM pipe, the entire draw call is processed in a single pass. So if an application were to send down an extremely large draw call with 10 million primitives, it would be bottlenecked by that draw call. It's going to digest that entire draw call before it moves on to anything else. Whereas in SWR, we chop up large draw calls into segments or into pieces then that can be each individually operated on in parallel. So we exploit some of the parallelism as opposed to bottlenecking by a large draw call. Front end, back end. The binning pass is back behind like I said, a single threaded front end on the LLVM pipe, whereas on SWR, the vertex processing and binning are really combined in a single pass that are threaded out. So we do utilize parallelization there. Primitive assembly and binning. The LLVM pipe uses a kind of a combination of JITted code as well as some hand-coded SSE, but then also scalar C, really to process all primitive assembly and binning. And that's all done one primitive at a time. Whereas in OpenSWR, we've exploited x86 intrinsics heavily to work on vectors of primitives at a time. So we do a lot of shuffling around of the vertex data to arrange it in a form where we can work on vectors of primitives at a time. So we get a lot of parallelization out of that. So almost a year ago, December of 14, we released the very first OpenSWR alpha package. We released that into open source. That was the SWR core rasterizer with a prototype OpenGL driver. It was kind of a homegrown OpenGL driver. And it supported roughly 1.4 equivalent OpenGL feature level. It was mainly used for getting just enough functionality to run the current versions of ParaView and Visit at the time, which were also utilizing 1.4, 1.5 level OpenGL. It was a fixed function pipeline. We used shaders underneath the covers, but we didn't expose shaders out at the API level, so the application couldn't really take advantage of that. As I mentioned, that is open source. It is still available on our website. It's really for reference though. But we've taken a kind of a course correction since then and released another level, Alpha 2 release in September of this year, which takes the same SWR core with improvements that we've been making over the last year. And it replaces the homegrown OpenGL driver with the MESA 3D driver stack. So it's utilizing the very latest MESA driver, which is the 11.0 release. It then provides us with OpenGL 3 level functionality. So in the course of about 9 months, we jumped up from 1.4 level functionality all the way up to 3.1, 3.2 level functionality. With that, we are able to expose vertex and fragment shader support and a GLSL language level of 130, which is equivalent, OpenGL 3. We are working on progressing that even further, but that is where we are right now. The main applications that we are focused on, as Jim mentioned in his talk earlier, ParaView, Nsight, and Visit. And we're happy to say that we've been working closely with them and supporting the very latest ParaView release that will be released here at the show, which is using OpenGL 3 functionality and shaders. We began discussion with the MESA community and a review process to get that source included into the MESA master tree. And in doing so, it is currently open sourced up on GitHub and has been open sourced and looked at as, like I said, we're discussing with the MESA community to get that fully integrated into the MESA master. So kind of a comparison of the two. The performance is still very good for OpenSWR, although in some cases we've lost upwards of up to 70% of our performance between the initial fixed function and the current SWR. And a couple of reasons for that. One is that we have some things we can still tweak. We have some things to tweak at the MESA level. We have some things to tweak at the SWR core level to fully exploit the best we can get out of kind of the workloads that we're interested in. Another is differences in shader code generation. As I mentioned in the Alpha 1 release, we used shaders under the covers, but we didn't exploit those. We exposed those out to the application. But by doing that, we were able to hand code those tuners for the fixed function pipeline that we supported. So we were able to make sure that they were very well-tuned shaders. Now these shaders are being generated and then compiled by the GLSL compiler. So we haven't done a whole lot to highly optimize those beyond what the shader compiler is getting us. We are we have vectorized those, so we do get parallelization out of them, but they're not as highly tuned as they could be yet. Another is that the SWR core has been maturing over the last year, and in that we have kind of upped the level of conformance that we can support, as well as different feature additions. And in doing so, we've lost a little bit of performance in trade-off for functionality. things that we're working to tune over time. But the functionality improvements were well worth the switch. Trying to write a modern OpenGL driver from scratch is a very difficult task. Trying to bring it from a fixed function stage to fully supporting shaders to then supporting OpenGL 4 and the very latest OpenGL is a large and daunting task. Why not take advantage of a very well-matured community that's out there with MESA and integrate our stuff with MESA? So that's what we've done. And as I mentioned, we're hopeful to recover most of this performance back through tuning. We have a lot we can still tune. We've been focused primarily on functionality at this point. So this is kind of an overview of how we fit into the MESA architecture stack. We've got a this is on the left there would be how the LLVM pipe driver sits underneath the application layer, the MESA state tracking API layer, and then the Gallium state tracking layer. And then SWR on the right, we've got the OpenSWR driver sitting on top of the OpenSWR core. And what we're showing down at the bottom there is that we are using the code from LLVM pipe. We're sharing that code for vertex and fragment shader generation as well as the texture unit. So we're using the mature code that's already out there to help us to generate those shaders. So we're going to take a little peek under the hood down below the driver of what makes the SWR core well suited for SDVis. Some of the features that make the SWR core highly performant is that we are very highly scalable. Core, as I mentioned earlier, features a threading model, as well as some of the fixed function rasterization units that will be used by any fixed function or any graphics pipeline. Still have some fixed function rasterization. It exploits a tessellation unit as well as stream out and up to 16x MSAA. The driver layer provides shader compilation and callbacks then that the SWR core will call back to those shaders. And the goal for the SWR core is to become a fully conformant, full-featured rasterizer, able to support any API with the appropriate driver written for it. So as I mentioned, OpenGL 3, OpenGL 4, you could even write other drivers to it. The SWR core API looks very much like a modern GPU. It's got a very modern API-like feel. It supports, it has device and context, features, state objects. It supports queries to get state back from the, back from the pipeline, and then there are draw functions for execution. It's really not much different than if you were writing a driver for any modern hardware GPU. So we almost think of the SWR core as a software GPU, and that serves as kind of the interface then on which we write a standard driver. So the OpenSWR driver that we have in the MESA stack is not that much different than any driver you would write for any of the hardware GPUs that are out there. Kind of an overview of the graphics pipeline, and anyone who's familiar with a graphics pipeline can see that really this isn't too different than any other graphics pipeline. We have a fetch shader, which does the input assembly fetch unit, vertex shading, tessellation unit with the hull shader, the tessellation shader, and domain shaders, geometry shader, stream output, binner, which assembles primitives then, rasterizer then, common rasterizer, pixel shader unit, as well as a back end that does kind of a flexible blend shading as well as output merger. So like I said, it's really not any different than a modern GPU implementation. So some of the front end features that, which is really kind of where we're the most unique from the LLVM pipe. I mentioned earlier, we have a common thread pool with n threads. Thread 0 is always always the API thread, and it takes API calls. Threads 1 through N then can work on either the front-end vertex work or back-end fragment tasks as those as necessary. All threads can participate in vertex processing. And I can't emphasize enough, this is one of our main differences from the LLVM pipe, is that all threads can work on vertex processing. And it's crucial for HPC and large scientific visualization tasks. And that draws get broken up into smaller draws. Currently, the vertex pipeline is fully vectorized to AVX2. We have some abstraction of SIMD, and our utilization of LLVM pipe gives us a pretty clear path for AVX 512 support. So we are working towards AVX 512 support, which is primarily for performance tuning. Our code will currently work on AVX 512 machines. It's just not as performant as you might expect. Sorry. The front end then also has primitive assemblers optimized for each type of primitive. So we're not trying to force all assembly through a common routine and doing a lot of branching. So we have a lot of optimization there for primitive type. Some other things, the vertex memory management is actually very low overhead. We only store enough information for vertex information for 8 primitives at a time. We use a custom arena allocator, so we're not doing a lot of alloc and free. We don't have a lot of overhead with garbage collection there. And the binning memory is actually very, very small. Some other kind of advanced culling techniques that give us a lot of speed, also necessary for HPC and SCIVIS, the very large triangle counts that you'd expect. We cull zero area triangles quite efficiently, very, very small triangles. Triangles that kind of fall between pixel centers, we will cull those. Like I said, very, very small triangles. And we're also very efficient at viewport and scissor culling. A couple other things that we are working on. We have a quick early rasterization phase that can be enabled to further cull primitives around pixel centers. And we've seen that in HPC workloads, upwards of 90% of triangles can be culled, can pass through this early rasterization phase, which allows us then to skip parts of rasterization and pass right on to the back end. Other ideas that we have in development are position-only shading, where we can skip some attribute shading as the pipeline is set up. We can defer other attribute shading, so we'll know kind of what is culled, what is clipped out, and so on, and not shade all attributes of all vertices, only those that are necessary. Another thing that we can exploit is NUMA awareness, so that we are aware of the topology of the system we're running on, and we can kind of target particular primitives to particular nodes as their memory latency demands. Some of our early results. Here's a graph of OpenSWR versus the MESA LLVM pipeline. And on the far left there, we've got a 3 million triangle scene. And in that scene, the scene that we're running here is a turbulence workload with a textured clip plane running through the middle of it over there. It was being run on an E5 dual socket system where each socket has 18 cores. It's running ParaView 431, which is a fairly modern version of ParaView, and it's running the OpenSWR Alpha 2. In the case of the 3 million triangle workload, we're actually 29 times as fast as the LLVM pipe. And then as we scale the number of triangles up, we've gone actually up in the 106 million triangle scene. we're 51 times faster than the LLVM pipe. So as you're seeing complexity increases, you can see kind of how some of our parallel features kind of get us a better advantage. On the graph below, this is scaling a 3 million triangle workload over number of cores. Obviously, the less cores we use, the lower our performance, but you can see that our progression is actually very linear. So we have very good scalability. A question came up to me earlier was, well, okay, well, do you just scale well over low triangle counts? And the answer is actually no. We scale very well over the higher triangle counts. So here we take the anywhere from 700,000 triangles, which is the lowest line in kind of dark blue, up to 33 million triangles, which is this is kind of a yellowish line at the top there. Scaling that over the number of cores, you can see that our scores, million triangles per second, actually do well in those higher geometry counts. This is a slide about the performance configuration. This was a standard system, like I mentioned earlier, 2 sockets using dual 18-core E5 Xeon processors, 128 gigs of memory total. There's a remark there about the NVIDIA coprocessor that was in that. It was not being used by us at all. It was in the system, though, as this system was being used to run some other benchmarks. But that coprocessor, the GPU, was not used at all. Early testing results. We are running the VTK C-test suites with both the OpenGL 2 backend as well as the OS MESA backends. We're passing at 99% of those tests. The OpenGL 2 backend on ParaView, passing those C-test results, 96%. Visit 281, we're actually passing their automated tests at about 85%. And we're working through a few bugs that we've got there that we certainly don't see any reason we can't pass those 100%. There are a few rasterization issues, as you would expect. So we may have a few pixel differences here and there, but we're resolving whether those are really issues or just kind of gold image differences. And also Nsight is doing quite well. Real usage testing has shown us that we've got a little bit of debugging to do, but we're well on the way to actually running that quite well also. Eventually we will start running, we will start improving our results though on the OpenGL conformance and MESA piglet tests, although our results are currently not very good because we don't support we don't export at least the geometry shader right now, and many of the tests require the geometry shader. Our experience, I think, as Jim mentioned earlier, we've got kitware that's going to be showing a demo of ParaView running SWR. You'll be able to see that, as well as they'll be talking in the lightning talks. We've got Visit from University of Tennessee. Alex got a demo down there. They can talk some too about running their experiences in their IPC talks. I don't think they're showing a demo here. But we do have a demo of Visit and SWR. And then Sean Ahern will be talking here in just a little while about the experiences of rendering in Nsight and SWR. And they've got the machine in the back of the room there, as well as a demo in the Supermicro booth. So I think I'm almost out of time, but let me go through our roadmap real quick. Is that basically we're working with the MESA community to get this upstreamed. And in doing so, we will be available in MESA Master once that happens. We're working on optimizing for AVX 512 KNL support. So we're also working on other optimizations that should get us better and better performance as we go. And we're also working to continually support other applications. The 3 that I mentioned earlier are kind of our main focus. Not to forget John Stone in the back there. We do run VMD. And it runs well there, but other tunings we also have. So we'll be picking up additional features and additional apps as we go. It is an standard OpenGL pipeline, so unlike other applications that may need to modify their application to support the API, we're already there. There's no recompilation necessary. It's just simply drop in library replacement and go. As I mentioned though, we offer a compelling advantage over the other standard MESA LLVM type software for large data visualization. We are fully supporting both the driver and as well as the core development. As I mentioned, Tim and I are the main OpenSWR developers. We have a few other folks within Intel that are working on the core, so it is a well-supported project. We plan to get it upstreamed into the master branch, and it does work with existing OpenGL applications with no code change required.